So first, starting off with the sampling rate, or some people may refer to it as the sampling frequency. And it's important for determining the maximum amplitude, as well as that we have a good waveform itself. We're describing it well in the time domain. Hopefully, what you see here as f of s, 1 over delta t. That's how we define it, the sampling rate. And this delta t, if you look at this delta t, these gray dots represent all the points that we're sampling this analog waveform. And hopefully you can kind of see the more points that I have, right? More samples, the better I'm going to be able to capture the amplitude of this signal accurately, as well as define the waveform itself in the time domain. So for example, if we look here, we're sampling here 1,000 times per second, and we can see that we're able to fully capture the amplitude. Here was a 1 volt signal. But once we get down here, we're only sampling 30 samples per second. Not only is the amplitude incorrect, but this doesn't really look like a sine wave anymore, which it should, a 10 hertz sine wave. Why don't we jump to a demo to try to drive home this point a little bit more?
You see a front end or a SCADIS piece of equipment that we make at Siemens here. And this piece of equipment is basically doing the conversion from the analog signal. The transducer comes into it, and it gets digitized in here, converted digitally and sent over Ethernet over to a computer to be viewed on the screen. So we don't see the analog signals on the screen. We see the digitized signals. And all our SCADIS units right here, they have something called a signal generator, a high precision signal generator. And what I'm about to show, I'm going to actually take the output of a signal generator so I know exactly the signal, and I'm going to plug it into the first data channel. So I have that physically set up here. And because I can control exactly the signal, we can play around with the the settings and kind of see what we get. Hopefully you learn something in the process. So that's physically what I have set up. I also have our software up here. This piece of software is called Spectral Testing. All right. And you can see the first data channel is turned on. It's set to vibration, but I can actually come in here and say, well, I don't want to measure acceleration with it. We'll measure the voltage coming in from this signal. So I'll pick voltage here in volts, 1 volt per volt. I won't even distort the volts or anything like that. And then I can go over to the next tab here. And here I have my signal generator. I can actually turn that on here. And I can say I want something like 4 volts, for example. And under more here, I can see what frequency. So I'm going to generate 100 hertz signal from my signal generator. And I'm going to make that at 4 volts. If I hit start source here, yoo-hoo! Do you see a sine wave, Charles?
Yes, I do. Very nice sine wave.
Yeah, it's looking nice. So let's think about this sine wave a little bit. Is it 4 volts? If I put a cursor on here and I double click, I can say move to 4 volts. Looks like I'm capturing the amplitude pretty accurately.
Mm-hmm.
Yeah, I'm digitizing this thing. And you can see there's a bandwidth here of 3,200. We haven't even talked about bandwidth yet. So for people that use our stuff, I go to Tools Options here. I can switch this, instead of bandwidth, I can display this in terms of sample frequency, which is usually twice the bandwidth being the highest frequency we can measure. So if I do that, the sample frequency is 6,400. That means 6,400 samples per second. And a lot of people will say hertz, and that's not really the frequency of the sine wave we're looking at. That's really, it's 6,400 data points per second. And I purposely, if we look here on the sine wave, I made it 100 hertz. So if I'm getting 6,400 samples in a second and 100 cycles in a second, so it's a 100 hertz sine wave, how many samples per cycle of that sine wave am I getting, Charles?
No, you're getting 64?
64. Let's let's see. So I'll hit start source here, and I'll zoom in on like one cycle here, and I can change the line style. I would ask the audience, Charles, but you insist on muting them so they can't participate.
I didn't know I could phone a friend.
Yeah. So, yeah, if you can see there's like a little cross here, there should be 64 of those per second. And it does look like a nice sine wave. Now, I think what Charles is talking about, we have to be careful about when we set our sampling rate, because, you know, the way the computer shows this is a little misleading. It connects the dots, right, with a line. So we think we might have a continuous wave, but really it's made of discrete bits or data points. So let's see what happens if I take my frequency up to 1,000. How many samples now will I get per cycle with the sine wave, Charles?
You'll be getting 6.4.
6.4. So let's see what happens to our sine wave when I hit. What do you think, Charles? Am I getting something pretty siney?
Yeah, it's a little jagged there. Not as nice as the first.
Yeah, a little jagged. And you can kind of see, like, you know, definitely now, the odds that I have a sample hitting on the right peak, I move this to 4 volts, it's a bit less sometimes, right? Like, yeah. I don't quite hit the peak. Yeah, 6.4, sampling 6.4 times the highest frequency of interest. I'm going to be off on the amplitude, at least as I view it from the time domain. Now over here, I think there's a button frequency. I can look at this versus frequency. If I do that, notice it's 4 volts. So what's interesting about this Fourier transform a little bit is even though I'm off a bit in the time domain, I'm still right on in the frequency domain, at least so far. Now, I think maybe we can zoom this up a little bit more. You want to pick a frequency, Charles? What would be kind of interesting? The highest frequency I can measure is 3,200.
Mm-hmm.
Yeah. So if I went to, I don't know, something like 2,800, let me try that. Let's see how bad it gets. What do you think of the sine wave now?
I'm not sure I see a sine wave.
Yeah, we're definitely missing some of the amplitude.
Go back to the presentation. I think the key point is hopefully clearer now after that demo, but this sampling rate helps us to determine the maximum amplitude and getting the correct waveform in the time domain here. And that delta T is basically the time between each one of our samples. So the next parameter here related to this time domain side of our illustration is the block size. When we talk about the block size, we're talking about the total number of points that are captured. So here it's represented by this cap in. And for example, it says a block size of 2,000 means we have 2,000 points that are acquired. And we're talking about acquired in this period of time, this cap T, which we'll talk about shortly. But here we can see the block size, there's 10. Right, the block size would be 10. So that's the number of points that we're capturing inside this cap T period, which is called our frame size. And the frame size is just the amount of data that we need to do one FFT calculation. And it's related here. We can see the frame size is related to cap in, our block size, times our delta T. So it's the total time period here would be the number of points times the amount of time it takes to measure each point. Now, we don't want to confuse that frame size, this cap T, with the total time to do our test, right? This cap T is just for one block of information. But let's say you wanted to do several averages, for example, and let's say our block size was such that it was 2 seconds. So we need 2 seconds of data just to do one average. Now, if we decided that we're going to, have 5 blocks of data, then we need 10 seconds worth of data to be able to do those 5 averages, right? Because each average itself has a frame size, or sometimes it's called the observation window, of 2 seconds. So don't confuse these two. Total time to do your test with whatever number of averages is different from frame size. We're just talking at this point of frame size, the total amount of time to get all those points on our block.